Okay, welcome to IMAC 685 MIS class, and today we're going to start talking about support vector machine. Uh, First, we go on to the course website and goes to the course module. Come down here to basic machine learning portion. I want you to download the support vector machine uh, Python example notebook. So this is what we our lecture today, and I have this notebook pulled up on screen for you. So download that notebook and pull it up and follow the today's lecture. We're gonna have spend some time on talking about last lecture period. We're dealing with the so-called linear regression, and support vector machine is basically a method of regression, but is using for different application. It mainly is performing classification. Basically, here you illustrated you have two sets of point, which is forming two cluster. We were trying to find a line in between, and which separates these two cluster of the point. So we basically classify one set of point with it's all on one side of the line, and the other cluster of the point, which is on the other side of the point, line. And not only that, the support vector machine method and trying to do is trying to find a line in between these two cluster, which is follows as far as possible to the closest point as possible. So the distance between these two closest point to the line on this line, and we call the margin, the maximum margin, which also we call the width of the separation hyperplane. So imagine this is a two-dimension. For three-dimension problem, we will have a so-called supporting hyperplane to to separate them, and instead of just a line. On the other hand, also the vector from the origin to the closest point to this line for both cluster we call the support vectors. So and the distance from the closest point to the center line, for the closest point to the center line, and we want that distance to be as large as possible. So it is still a very similar regression problem, but now becoming instead of a continuous linear regression problem, now can be becomes a combinatorial problem, which line is which point is the closest when you change the slope of the line, and the closest point might change if you tilt this line that way, and this point and that point may be becoming the closest point. So how do we formulate this as an optimization problem, and how will we solve it? And we just go through some of the basic concept. First, we review some of the concept from your matrix theory, and basically if I want to project a vector onto a b vector, so it should be a dot b divided by the length of the b, which is the length of a times the cosine of the angle between a and b. So we call this projection. So this portion of the line represented by the projection. Similar situation we start talking about if the point is a positive example, for example this point right here, this point from the origin, this is the support vector. Okay, this is for support vector, And then we project that onto a perpendicular vector we call the omega 1, and project that onto the omega 1. So this blue vector represents what omega 1 dot product of x1. So it's basically a times b times cosine theta. Okay, and that's what it is. Similar situation, if this is a negative portion, this is the support vector from the origin to this x2 point, and omega 2 is this supporting vector, which is perpendicular to the center line, and I have project x2 onto this omega 2 will be omega 2 in the product of x2. So any point within is the same thing, okay? So here we have, okay, this is the point when x is positive, omega 1, omega dot product of x plus b is greater than 1 in that case, greater than 1. So this is basically the equation. This is omega dot product x of the negative portion, which is x2, plus b is less than or equals to negative 1. So here is the equation. So further, we're going to start talking about a y decision variable. And y decision variable is kind of called binary. Either is positive or negative 1. Either for the positive example or for the negative example. So if I multiply the y onto this equation, omega times x plus b is always greater than 1 on both sides. So adding these binary variables, either positive 1 or negative 1, we're getting a equation like this, two inequality equation. And we can simplify that. Basically, we say the coefficient to a single equation, either y times omega dot product of x whatever, and plus b minus 1 is equal to 0, basically. So this will summarize these two equations, make it to one together. The next what we're talking about is we need to address the process by calculating the maximum margin, we call it width. And basically, if I have two closest points, one hitting on one of the boundary, the other one hitting on the other boundary, those are the two closest points, maybe, let's see, maybe this point and that point, okay? Or we're talking about one of those, two of those, these point and that point. So one we call the x plus, one we call the x minus, which is closest point to this center line, and for both sides, and we'll call it x plus or x minus. The difference of vector x plus minus x minus, which is this vector right here. Then we do the projection onto the omega. Omega is a vector actually perpendicular to the center line, and whatever length is that, we call this width. So basically what we do is the width is x plus minus x minus divided by, multiplied by the omega divided by the size of the omega. So that we normalize it. Eventually we can determine, after a few simplification, the width of this region will be defined as 2 divided by the length of omega. The omega, which is the magnitude of the omega vector. And we formulate this as a optimization problem. Should be maximize the width. We're trying to find a hyperplane, supporting hyperplane, actually maximize this width in between these two set of points right here. Okay. So that's my and we can even simply convert it into the minimization of 1/2 of omega squared. So we get it directly a optimization problem for minimization 1/2, which is his first derivative, it just equals to x. Okay. So this is a pretty straightforward equation, and we're not going to introduce to all the equations. Finally, we can formulate the support vector machine problem into a nice form of minimization problem with alpha as our decision variable, and it is a so-called quadratic problem. So here we have is x is the coordinates of all the input point. X is the coordinate basically input and out. X here is, for example, this is x1 and x2. It's 3-dimension x1, x2, x3. So x will be my input data. So x transpose times x will be my quadratic term. And first is the alpha is 1 times alpha will be the the linear term. Okay, and so alpha is my solution. And here what we have coming into talking about Python code, how to carry out solving this optimization problem. Okay, how to solve this optimization problem with using a Python code. We can also first we can either manually implement this as a solution, since we can find its first derivatives, and then based on certain criteria, which is what we have right here, the subject constraint, we can form our own constraint optimization problem using Lagrangian relaxation model, which basically we relax these two constraints, adding a Lagrangian multiplier, forming an unconstrained optimization problem in that case. So here is the implementation of this particular method to solve using Lagrangian relaxation. I'm not going to go through the detail of the algorithm, and this is manually implemented, and I can figure it out. And also I'm using a randomly generated set of x and y, and basically x, capital X, is the coordinates of the input. I'm using the sklearn data set called MachineLearning. Basically it creates a random set of a point, and you tell them I want to send to center, which means to cluster, and sum of the randomness and cluster standard deviation 0.6. So it randomly scatter and around. So these are the 2 points, and also I'm accessing y as either they represent one cluster or the second cluster, cluster 1 and cluster 2. So instead of using this so-called MachineLearning, the first cluster is supposed to be called 0, second cluster is called 1. I'm going to make it as a first cluster called -1, and the second cluster is 1, and that's this part of the code represents. Okay, so it's fairly simple and so far, and we can actually, let me execute that a little bit. Okay, and after I execute it, I can show you what is x looks like. So x is a set of points which each one has 2 coordinates. This is x1 coordinate, this is x2 coordinate, and I have 250 of them. Okay, I can also take a look at y. example, y is a single vector, represent these points, represent which cluster. -1 represent first cluster, 1 represent the second cluster. So right here, we give you the x and y. What I mean, capital X is actually the coordinate, which is x1 and x2. All right, let's move on. And we can plot these two clusters with a different color, which is y is the color, -1 is one color, 1 is the other color. Okay, so you see that right here. And I'm going to split that into training and testing region. So we randomly select 70% as a training a set of x and y, and test, which means 30% as the test for later on we see how well our cluster. So this is the training test split, which is also part of the sklearn model and called model selection portion. It's called train test split. So this is a very neat function, and sklearn help you to generate your data and split them into training set of x and test set of x, y, and so on and so forth. Okay, and you can tell them what is the you can tell them what is these are all the training tests, and test size is a percentage. For example, random C, you give them a specific random C, how to choose that. For here, we call it actually one third of them as a test set, and 2/3 of them are the training set. So by default is training size. I think default is default size is 30 and 70. So we separate these two, and you can see the training set. Therefore, I'm going to forming a class called SVM, and I'm going to call that SVM to solve. Create a class SVM and fit them with the training X and training Y only. So this part is using the training set to illustrate how the the center line is, what is the maximum region according to the fitting. So I just want you to understand this algorithm of fitting portion is just 2 lines of code. Of course, this is a little bit involved how to solve using a regular optimization problem, Lagrangian relaxation problem, which is straightforward as well. But once you've done that, we can basically forming the random set, which is input data, and just fit it. And okay, after 8 iteration, it converges to the the proper gap, and then we can use this to plot the scatter first using 2 different color to separate them, and plot the line, plot the also the dotted line, which is represents the maximum width. After that, we can test how this separation predict on the test set. So what we do is using the prediction function in the SVM module we just class we just created, and now we put it in the X-test. X-test is the set of the testing data set. We didn't use it to train the original support vector machine, and we calculate based on this separation hyperplan, see if we come up with a prediction. the prediction, which is either -1 or +1. So then we illustrate, print out the confusion matrix. The confusion matrix basically is the diagonal element represent the correct classification. So these are meaning if the Y is predicted as a class 1 and is correctly predicted in the set. So basically we could compare the Y test into the Y predicted based on the X test. So if they come up the same, then this is correct, either for cluster 1 or for cluster 2. The off-diagonal element represents the incorrect prediction from our model, which right now for this set of data it is 0. So there's no incorrect prediction. So this is a fairly simple problem using manually implemented SVM. I'm going to conclude this lecture video, and I will start talking about using the so-called scientific kit learning library. They have built-in function, 2 different versions, how to do that using the scientific kits library. Okay, I'm going to conclude this video for